Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element Berkelium. I think this photo needs a bit of explanation. What you see here is a microphotograph of the first isolated bulk sample of berkelium metal. Calling this a bulk sample may be overstating things a bit. While it is a large sample, it's only 100 microns across. That's 1/10 of a millimeter. Just barely visible to the unaided eye. Compared to a human hair, it's only about twice as wide, and it weighs only 1.7 millionths of a gram. Here we see Theodore Gray's beautiful periodic table. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. Berkelium is the 97th element in the periodic table. Its atomic number is 97 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. Dmitri Mendeleev, often considered one of the fathers of the modern periodic table, was trying to make sense of how the elements related to each other. He was smart enough to know that he didn't know everything. His table, originally published in 1869, left room for future discoveries by leaving spaces for as yet undiscovered elements. In our case, he left a space for berkelium after the also as yet undiscovered neptunium, plutonium, americium, and curium. But that's the end for this version of the table. Like all the elements in this part of the periodic table, we don't have to go back in history very far for the discovery of berkelium, only back to post-World War II research performed at the University of California, Berkeley. Berkelium was co-discovered by this group: Kenneth Street Jr., Stanley Thompson, Glenn Seaborg, and Albert Ghiorso. I love this photo. You don't often get a picture with all the discoverers together. Seaborg received a Nobel Prize for his work. An element was named after him, Seaborgium. This was a bit controversial at the time because it was traditional to only name elements posthumously, and Seaborg was still alive. Here he is pointing to his element. Seaborg discovered or co-discovered a total of 10 elements. Albert Ghiorso was involved in the discovery of 12 elements, more elements than anyone else, though he, unfairly in my opinion, never received a Nobel or had an element named after him, although Ghiorsium was proposed for element 118 but not adopted. I hope he's considered in the future. They used the new 60-inch cyclotron built by Ernest Lawrence at the UC Berkeley Radiation Lab, later called the Lawrence Radiation Lab, and even later the Lawrence Berkeley National Lab after the word radiation became too politically sensitive for Berkeley. In the accelerator, they started with Americium 241, which itself had been created much the same way 5 years earlier from plutonium. The accelerator is used to produce a stream of alpha particles. Remember, an alpha particle is a naked helium nucleus consisting of 2 protons and 2 neutrons. When these alphas hit the Americium 241, you get Berkelium 243 and 2 extra neutrons. Making berkelium like this with a cyclotron is a slow, expensive, and not very productive method. It's much more efficient to produce berkelium in a reactor, though the process is a bit different. Here you see the high-flux isotope reactor at the Oak Ridge National Lab in Tennessee, which began operation in 1966. This reactor was designed to produce isotopes, not generate power. A 22 milligram batch of Berkelium-249 was prepared over 250 days at Oak Ridge for scientific research. We'll see this again later. A total of just over 1 gram of berkelium has been produced in the United States since 1967. 1 gram is about the mass of a paperclip. Let's see the process in a reactor. We'll start with uranium-238, the most common form of uranium found in nature. Uranium-238 has a half-life of 4.5 billion years, so we don't have to worry about it decaying away during this process. Remember, in a reactor, there are lots of free neutrons available from the fission process. Eventually, our uranium-238 will be struck by a neutron and changed into uranium-239. Uranium-239 has a fairly short half-life of only 23.45 minutes. This shorter half-life is good because the next step depends on its decay by beta particle emission to neptunium-239. Also with a short half-life of 2.356 days, which is good news since we need it to decay by beta particle to our next target, plutonium-239. This first part of our berkelium journey is also how they produce plutonium-239 for reactor and weapons applications, but we've only begun. Our plutonium-239 has a half-life of just over 24,000 years, so, like the starter uranium-238, we don't have to worry about it decaying away during the process. Eventually, our plutonium-239 will be struck by 4 neutrons. I won't detail these individual steps, and it's changed into plutonium-243 with a short half-life of 5 hours. This will decay by beta particle emission to Americium-243 with a longer half-life of 7,350 years. This new element absorbs yet another neutron and becomes Americium-244. Americium-244 has a nice short half-life of 10 hours, which is also good news since we need it to decay by beta particle to our next target, Curium-244, with a half-life of 18.11 years. We're not done, but we're getting there. The Curium-244 then absorbs 5 neutrons, eventually becoming Curium-249 with a half-life of 64.15 minutes. That new isotope of curium decays by beta emission, finally to Berkelium-249 with a half-life of 327.2 days. As we'll see, this isn't the longest-lived isotope, just the easiest to make in quantity. Incidentally, that berkelium decays by beta to the next element up in the periodic table, Californium-249, so you'll probably be seeing this slide again next month. Since this element was first created at the Berkeley Radiation Lab, it was given the name Berkelium after the city of Berkeley and the University of California, which ran the radiation lab. Another reason, or excuse, to give the element a place-based name was the previous element names were based on the lanthanide element above, so Americium was similar to europium, both confederations of states. Curium was named after a scientist, and it was underneath gadolinium, named after Gadolin, a Finnish scientist, which placed berkelium under terbium, named after the town Ytterby, where it was first found. This tradition was not continued after this, since it constrained the element namers. It's really hard to find pricing for this stuff up near the high end of the periodic table. You can't get it on Amazon, and the only value I could find was an eye-watering $185 billion per kilogram. And of course, that would be a bad investment since it and your money are decaying away all the time since it's radioactive. Our tiny 1/10 millimeter sized piece from the beginning of this episode would cost over $300,000, and I think that may be a gross underestimate considering what it took to make that 1.7 microgram piece. Berkelium is a member of the actinide series of elements down at the bottom of the table. It's the 9th element of the actinide series. The elements of this series are chemically similar to the row above, the lanthanides. All the actinides and their isotopes are radioactive. Let's look at isotopes. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 97 protons for berkelium, but there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different masses. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 19 known isotopes of berkelium, and as I mentioned in the previous slide, we've reached the portion of the periodic table where there are no stable isotopes. All the isotopes of berkelium are radioactive. We don't really find berkelium in nature. The word isotope comes from the Greek, isos meaning same or equal, and topos meaning place. You've used a topographic map to find your place, I assume. All these various isotopes of berkelium occupy the same place in the periodic table. Of the isotopes of berkelium, these are the longest lived, the ones with half-lives over 1 hour. More on half-life in the next slide. The longest berkelium half-life is berkelium-247, with a half-life of only 1,380 years. That's why it's not found in nature. Given the 4.5 billion year age of the Earth, all the primordial berkelium has decayed away. It has to be manufactured, as we've seen. All radioactive elements decay and transmute into other daughter elements, something the ancient alchemists dreamed about, but didn't know was happening around them all the time. Although I'm simplifying this a bit, atoms can decay by alpha or beta decay. I want to show you the decay series of berkelium. First, let's look at what alpha and beta decay look like on this chart. We're only using a very small portion of a much larger chart. On this chart, the horizontal axis shows how many protons plus neutrons are in the nucleus. This is related to the atomic weight of the isotope. The vertical axis is the number of protons in the nucleus, its atomic number. Since the atomic number also tells us what element we're dealing with, each row is one unique element. As I mentioned, when an isotope decays, it can do this by emitting an alpha particle or a beta particle. An alpha particle is made up of 2 protons and 2 neutrons. 4 particles in total. So if we start with something like radium-226, it has 88 protons. All radium isotopes have 88 protons. It has 226 protons plus neutrons, giving it an atomic weight that puts it in this column over the 226. Radium-226 decays by alpha emission, meaning it loses 2 protons and 2 neutrons, 4 particles in total. This means we need to move 2 rows down for the 2 protons and 4 rows to the left for the 4 total particles. You can see we arrive at radon-222. Okay, this is the move for alpha decays. What about betas? Here, one of the neutrons in the nucleus becomes a proton and an electron, and the electron is spit out of the nucleus as a beta particle. This means the nucleus gains a proton, but does not change its atomic weight significantly, since electrons are very, very light. This time, we'll start with thorium-234. Gaining a proton, but not changing atomic weight, moves us up one row, and we now have a new element, protactinium, but with the same weight, 234. This is what beta decay looks like on our chart. Now let's get to the berkelium decay series. As berkelium decays, we'll see it transmutes into other elements. After a few decays, which I'll detail, we'll arrive at uranium-235 and a decay chain we've seen before called the actinium series, because it contains actinium. We'll start with berkelium-247, the longest-lived isotope. For the first few decays, I'll put the isotope decay mode, alpha or beta, and the half-life at the top of the screen. Berkelium-247 decays by alpha to Americium-243. This decays by alpha to Neptunium-239, which decays by beta to Plutonium-239. Remember, we move up one row for beta. Plutonium-239 decays by alpha to uranium-235. At this point, we've already seen the rest of the decay series in previous episodes, so I won't bother you with the details. Through a series of transmutations, the uranium-235 eventually decays to lead-207, which is stable and not radioactive. If you want all the details of the actinium decay series, check out the Tales from the Periodic Table episode on uranium here. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any radioactive isotope. I chose 1,024 atoms because it's a power of 2, and we'll be doing a lot of divisions by 2. If we wait one half-life, one half of your isotope will decay, and we'll have 512 atoms left. If we wait one more half-life, half of that remaining half decays, leaving us with 1/4 of the original 1,024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, we'll have about 1/1000th of our original amount. By the way, notice there's one remaining atom after 10 half-lives. If we waited one more half-life, our remaining atom would have a 50-50 chance of decaying in that time. Since we're on our 13th radioactive element, 14th if you include bismuth, I'd like to repeat how radioactivity is measured. There are 3 interesting facets of radioactivity we should pay attention to. First, we might want to know how many disintegrations per second a given source gives off. This is a measurement of its radioactivity, the rate particles are emitted. This is probably the simplest thing to measure. You can use a simple Geiger counter and just count the number of detections per second. But you need to take into account the size or area of the detector and its distance from the source, and multiply the measured counts per second as if your detector could completely surround the source to catch all the disintegrations in every direction. The international unit for this is the becquerel, named after Henri Becquerel, who discovered radioactivity. 1 becquerel equals 1 disintegration per second, so most sources are in the kilo, mega, or even gigabecquerel range. In the US, we also use an older unit, the Curie, obviously named after our dynamic duo Marie and Pierre Curie. 1 Curie is the amount of radiation given off by 1 gram of radium. Radium was discovered by them, get it? 1 curie is 37 billion disintegrations per second, or 3.7 times 10 to the 10th becquerels. Radiation carries energy, and that energy is deposited in your body or into any object the radiation hits. The next unit measures how much energy is absorbed per kilogram. This is called the absorbed dose. In the metric system, energy is measured in joules. 1 joule is about the amount of energy used to lift an apple from the floor to a table. The international unit for absorbed dose is the Gray, named after Lewis Harold Gray, a physicist who worked on the effects of radiation on biological systems. A Gray is equivalent to 1 joule of energy absorbed per kilogram. This is quite a bit of radiation, so you'll usually see units of milli or micrograys or something like that. In the US, we have used the unit of the rad, or radiation absorbed dose, which is 1/100th as large as the Gray, but still a large amount of radiation. Lastly, we want to know how this absorbed energy will affect you, and that will depend on the type of radiation, alpha, beta, or gamma, which bodily organs are exposed, and how sensitive these body parts are to the specific kind of radiation. This is called the effective dose. The units here are the sievert, named after Rolf Maximilian Sievert, who was a medical physicist. He studied the biological effects of ionizing radiation. In the US, we also use the rem, which stands for Radiation Equivalent Man. The sievert is just 100 rem, and the rem is 1/100th of a sievert. These are human health-based units. They take the absorbed dose and adjust it as an indicator for the potential for long-term health effects, such as cancer, genetic damage, etc. The effective dose is used to set limits on exposure for radiation in the home and workplace. For instance, you are allowed to be exposed to 50 millisieverts or 5 rem per year in the workplace. You normally absorb about 67 millirem every year from the environment around you, and that depends a lot on where you live. That's 1/75th of the allowed annual dose. A dental X-ray exposes you to about half of a millirem. A standard chest X-ray, front and side, exposes you to up to 10 millirem, and a chest CAT scan gives you up to an 800 millirem dose. Although radiation exposure always carries some risk, with medical X-rays or CT scans, the benefits should always outweigh the risk. I normally talk about the abundances of the elements on this slide, but because of the relatively short-lived radioactive nature of berkelium, at least compared to the age of the universe, there's not much to say here. There's really none to speak of in the universe, having all decayed away by now, and none in the sun. Likewise, none in meteorites, or in the crust of the earth. It's absent in the oceans, and of course, thankfully, none in us. That was a lot of red X's. We can talk a bit about a few physical properties of berkelium, but not a lot is really known about this rare element. As you can see, most of the properties have an Na, not available, next to them. Still, there are a few things we do know about berkelium. Berkelium has a density of 14.78 grams per cubic centimeter. It's a fairly dense element. As a reminder, the density of water is 1 gram per cubic centimeter, and here are a few more densities of some of my favorite other elements and compounds for comparison. You can see berkelium's density is significantly higher than lead at 11.34 grams per cubic centimeter, but lower than tungsten at 19.25 grams per cubic centimeter. Here's a graph of the elements from highest density to lowest density. I have a set of blocks so you can feel density for yourself in my live talks. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, and magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, berkelium's density is 14.78 grams per cubic centimeter, near the top of the chart, the 13th densest element, a little higher than the density of mercury. Berkelium has a melting temperature of only 1,259 degrees Celsius. That's 2,299 degrees Fahrenheit. That's the 46th highest melting point, about the middle of our chart, around the melting points of gold and silver. Berkelium boils at 2,900 degrees Celsius, 5,252 degrees Fahrenheit, giving it the 36th highest boiling point of all the elements, above average on this chart. That's 1,641 degrees Celsius above its melting point, giving it a smaller liquid temperature range than some of our recent elements, such as uranium, neptunium, and plutonium. Please refer to their videos. One of the subscribers to this channel, SillySad3198, thought it might be nice to see a graph of liquid temperature ranges from highest to lowest. So here it is. The widest liquid temperature range is of neptunium, with a 3,356 degrees Celsius liquid temperature range. As I mentioned, berkelium's liquid temperature range is a little higher than average, with a 1,641 degrees Celsius range, the 39th largest liquid temperature range of the elements. The smallest liquid temperature range belongs to neon, which is liquid in only a 2.51 degrees Celsius range. Notice all the noble gases, and hydrogen, have very small liquid temperature ranges. The size of the berkelium atom is around 340 picometers in diameter, about 3.2 times the size of the hydrogen atom. Here's its electron structure. By the way, a picometer is a trillionth of a meter. Atoms are stupefyingly small. Looking at all the element atom sizes, here we see them sorted from largest, cesium at the top left, to smallest, helium at the bottom right. The size of the berkelium atom places it in the middle region of the chart, about the same size as palladium or lithium. Here's the periodic table of the spectra. If you excite atoms, they give off specific colors of light. This is the spectrum of berkelium. It has a moderately simple spectrum with a smallish selection of colors. Notice there seems to be some missing regions of color, oranges and cyans specifically. There are strong reds, greens, and blues. Putting berkelium in a flame, don't do that, would make these colors of light. When these colors are combined, they would probably look whitish, since adding red, green, and blue light gives you what looks like white light. See my video about color mixing for more on that subject. Spectra of the elements uniquely identifies them to scientists, as each element gives off its own unique set of colors. Spectroscopy is one of the most powerful tools of science. Okay, I know, you're thinking, we're getting pretty high up in the periodic table. There can't be that many applications for berkelium, and you'd be right. The only application of this element is in the creation of other elements even higher in the periodic table. I mentioned near the top of this presentation we'd see this photo again. Although you really can't see it, at the tip of that test tube is a 22 milligram sample of berkelium, one of the largest quantities ever made at one time. It took 250 days to make this inside the reactor at the Oak Ridge National Lab at a cost of about $1 million. This sample was used in the production of element 117, tennessine. Making tennessine begins with berkelium-249. high-energy calcium-48 ions, element 20, are produced and accelerated. The accelerated calcium ions are fired at the berkelium target at high speeds. In rare instances, the nuclei of calcium and berkelium fuse, forming a highly excited compound nucleus with 117 protons, the atomic number of tennessine. This compound nucleus then sheds excess neutrons to become a more stable, albeit very short-lived atom of tennessine, with a half-life of only about 80 milliseconds, less than 1/12 of a second. And that wraps up the berkelium applications. As usual, we'll end this talk with Mary Soonley's elemental haiku about berkelium. Face the firing squad. Yield exotic elements under bombardment. In the next program in this series, I'll examine the element Californium. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about the element berkelium. For more Tales from the Periodic Table, see this playlist on my YouTube channel. And of course, I'm required by law to say this, smash that subscribe button.